All right, welcome back everybody. So last time I told you that this video was entirely skippable and you will lose next to zero context if you do. So feel free to go ahead and skip the video if you don't want to sit here and memorize terms for the next 15 minutes. But yeah, feel free to come back to this video when you have a little more context and when you feel like you're ready to pick up some extra definitions. So for this particular video, yes, we are giving a whole bunch of definitions and it can be very dry, but bear with me here. The reason why we are going through this section is to we're not just classifying differential equations just for the hell of it. We are classifying differential equations so as to give ourselves a measure of how difficult they are to solve. So not only are we categorizing these guys, but there are measures of what a hard equation is or what a difficult equation to solve is. And in that vein, the first thing I want to point out is that there are two different kinds of differential equations that we come across in practice. There are ordinary differential equations, which where the functions involved depend only on one independent variable. There can be many different dependent variables, but all of them depend on one single solitary independent variable, usually a time or a spatial variable. But the only derivatives you see are ordinary derivatives. Now, there are what are called partial differential equations as well. In this lecture series, we will not be talking about partial differential equations, but I'm assuming at some point I'll be making a partial differential equations playlist as well. So be on the lookout for that, or tell me what you'd like to see in the comments in such a playlist. But the idea is that we are making sure that everything we study in this lecture series only revolves around a single independent variable. So yes, we can talk about partial differential equations, but that will be for another time. So let's see about how we can start classifying these ordinary differential equations, these ODEs as they're called. So the first thing we would like to note is, well, come on pencil, work with me. We can go ahead and start by saying, okay, what we studied the last couple of videos are differential equations that take this form, where there's one derivative and it's a first derivative. And there are no other derivatives in the equation. So in this case, because the highest order or the highest derivative that appears is the first derivative, we call this guy a first order differential equation. So a first order ODE. Right, there is such a thing as a second order ODE. And that would mean that we could talk about equations that look like this. Minus 2y prime plus a 2y equals 5 sine of t, whatever. Right, the order in this case is going to be, again, the greatest number of derivatives you have to compute for your dependent variable. So in this case, the highest derivative that appears is a second derivative, so this is a second order ODE. Okay, so there's that. And in some sense, the order of a differential equation gives us a measure of how difficult it is to solve, right? The more derivatives you have to compute, the more subtleties there are to the kinds of functions that can solve the equation. But we can go even further. That's not the only measure of how difficult an equation is to solve. We can also talk about whether or not your rate function, right, dy dt equals f of ty, we can go ahead and scrub the t out of that equation entirely. And when we do, supposedly that makes things a little easier to solve because this thing is instantly a separable equation. Right? So dy dt equals just a function of y. We will go ahead and call this an autonomous differential equation. And it just means that the rate function is completely independent of the time variable. And usually this is specifically for temporal systems. So when your independent variable is a time variable specifically, we talk about autonomous systems in that way. Usually we don't have a context for spatial dependence in this setting. But usually that was the case for your Calc 2 classes, right? You're solving a function and saying, okay, what function has this as its derivative? Well, it means you're going to have to figure out what is the antiderivative for that function. So usually that's the context for the corresponding spatial condition. But if our function happens to depend on this time variable as well, then we're going to go ahead and call this a non-autonomous differential equation. Okay, just means that it's telling you whether or not your rate function depends on time. Great. Now, an ODE, and be very careful with this notation. It's very, very loaded. There's all kinds of stuff that could go wrong with this definition. But observe that our ODE can always be put into a general form where you're just saying that you have some expression of y, its derivatives, and the independent variable t that you can set to 0. And that even goes for this guy up here. If I just move this over to the other side, then there, I have a function g of t, y, y prime, and y double prime that I can set to 0. And that's what my differential equation looks like. It's basically a level set of some function. But, in fact, it's the 0 set for some function. But it's a little tricky to deal with this guy when you include the time variable. What we usually like to do instead is keep it in that form. So this y double prime minus 2y plus 2y equals 5 sine of t. I'm going to go ahead and just put all of the y pieces on one side of the equation, and this will be some function little g of t on the right. And this actually helps us to kind of organize the complexities of the equation into more manageable pieces. And specifically, what happens in this case is that I can go ahead and talk about what happens to these variables, to y and its derivatives under this function f. Now, a very specific brand of equation that we're going to be very, very much trying to understand in its entirety here is a linear differential equation. And this definition, I'm not even going to bother writing down because it's already over here on the left-hand side in the notes. So feel free, pause the video and take a look at the definition here and see if it makes sense to you. And when we come back, the idea is that a linear differential equation allows us to split our function into smaller chunks, that the function of a sum is equal to the sum of the individual functions that we put in. And also, likewise, if we substitute a scalar multiple of our function u, then we can factor out that u from the function. So think about this in terms of, say, matrix multiplication. So a matrix of, I don't know, lambda v plus w. Well, you know that you can go ahead and distribute the multiplication across the sum. That is a linear operation, right? Distributing across a sum, that's linearity. And factoring out a lambda here, a times v, just means that the same thing. This is what we call a homogeneity, right? Being able to factor out that term. But the idea is that instead of looking at what A does to this entire combination, we just have to know what A does on the individual vectors v and w here. And then we can go ahead and play with the pieces afterward. So instead of multiplying A into lambda v plus w, we just need to know what AV and AW look like, and then combine those pieces. And that is a linear differential equation where you can go ahead and factor these pieces out. And we'll go ahead and walk through some examples. For example, up here, this is an example of a linear differential equation, right? If I were to go ahead and say y equals u plus v, then look what happens. This is u plus v double prime plus twice u plus v prime, or sorry, minus 2, plus twice u plus v on the left-hand side, right? This is what I'm going to call that big F function. But notice the derivative is linear, right? This guy will actually distribute across sums, so I can bring that double prime inside. I can go ahead and subtract twice u prime plus v prime, and then plus, oh shoot, I should put that on the inside. So this is minus 2u prime plus 2v prime. Then I'll have a plus 2u plus 2v. And I can go ahead and separate these guys out into u and v pieces. So u double prime minus 2u prime plus 2u, and then plus v double prime minus 2v prime plus 2v. And this is exactly f of u, u prime, and u double prime, plus f of v, v prime, v double prime. So I can go ahead and split my sums so that they look like the original function, or the original big F, right? And that's what a linear equation is. I can also do the same thing for a scalar, and I challenge my audience to go ahead and do that, prove that to themselves, that if I were to put this in, y equals some constant, lambda times u, then f of lambda u prime, lambda u prime, and then lambda u double prime is actually equal to lambda times f of u, u prime, u double prime. And that would be for this definition of f. I challenge you to figure that out, or to prove that one to yourself. Okay, so if our function happens to not satisfy that sort of a relation, where, say, like I had sine of u plus v here, well, this is definitely not always equal to sine of u plus sine of v. And if you thought that, shame on you. Go check out, go review your trig. But that's the idea, that this is a nonlinear relation, or a nonlinear function. And this is probably the largest designation that we can make, the most important designation we can make for a differential equation. And the reason being is the following. Linear equations can use linear algebra. Right, and that's the biggest thing that we are going to use here. Right, the biggest treatment, or the biggest reason why certain equations are harder to solve than others is because they are nonlinear. And you'll hear this all the time: nonlinear equations, nonlinear differential equations, nonlinear systems. They are ridiculously hard to solve, notoriously hard to solve. And that's simply because our understanding of algebra beyond linear systems, like we know it, but it's very much a theoretical study, right? We know nonlinear objects from a theoretical standpoint more than from a practical standpoint. And we've spent the better part, if I remember correctly, the history behind this, we've spent the better part of 3 centuries trying to understand the nonlinearity and the behaviors that are associated with it. And there are all kinds of different reasons why nonlinear systems are ridiculously hard to solve, not the least of which is that sometimes they create what are called chaotic dynamics. Again, I'll refer you to the dynamical systems video playlist for more on that. But I digress. Once we have this linear dichotomy, we have linear equations, and we also have, for linear equations, remember, if you had any linear algebra, remember that we were trying to solve equations ax equals b. This system, ax equals 0, always has at least a trivial solution. And in fact, because this is such a nice system, we give it a name. This is the homogeneous system. Right, so it's a homogeneous equation. And the same thing goes for differential equations. F of y, y prime, y double prime, and so on, out to yn derivative. If I set that equal to the 0 function, then we have a homogeneous differential equation. If the right-hand side here happens to be a function of t, a non-zero function of t, then this is non-homogeneous. And no, I'm not mispronouncing that. There are 2 e's in this word, okay? It's not homogeneous, it is homogeneous. And I am a stickler about that. If I ever hear any one of you say homogeneous when you mean homogeneous, I will disown you. Okay, now that we have that clear, let's see. Let's give a couple of examples here. So we have the terms in place, and I will actually just go ahead and leave this. The video is getting a little long already, so I would like to just go ahead and put this up on the screen. Feel free to pause and read through the notes here to get a better idea of our classification. And I'll scroll down here so you can see this half as well. Yeah, we'll do this right here. So there's the other half, and that's going to be the end of this section, right? We are officially done with this section, and I just want to make sure that we make one thing very clear. That linear equations are probably the easiest thing for us to solve, but that does not mean that they are easy to solve. That's why we have an entire class dedicated to solving linear equations. And that is the vast majority of what we're going to be studying for the rest of the lecture series. Linear equations are hard enough to solve as it is. The second thing that we're going to use to distinguish the complexity of our equations is the order of the equations. So our first order of business, no pun intended, is to talk about first order linear differential equations. And that will be the beginning, that'll be our next video. And from there, we're just going to talk everything that we can about first order equations. And once we exhaust that, we'll start talking about second order equations. There's a reason why we don't go into third order, fourth order, fifth order, and we'll explain that when we get there. But we are going to be studying linear